Welcome to the Explainer. Today, we're going to totally demystify the physical world right around us. We'll take those everyday mysteries you see right outside your window, especially on a classic sunny Ugandan afternoon, and uncover the invisible science that's making it all happen. If you've ever wondered how the physical world actually works at a microscopic level, well, you're in the exact right place. Let's get right to it. Here's our roadmap for today's zoom-in journey. We'll be hitting 1. Meet the matter around you. 2. Properties of the states. 3. The kinetic theory explained. 4. Heat gain and heat loss. And finally, 5. The cooling magic of evaporation. We're starting big with everyday objects and zooming all the way down to invisible moving particles. Okay, before we get too technical, I really want you to think about this. What do a lump of ghee melting in the afternoon sun, a wet school uniform drying on a wire line, and the sweat on your forehead after a quick run, what do they all have in common? I'll give you a hint. The answer completely relies on understanding the fundamental building blocks of our universe. Section 1. Meet the matter around you. So let's lock down exactly what we mean when we talk about those building blocks. It all comes down to one word: matter. Matter is simply defined as anything that occupies space, so it has volume and has weight or mass. Basically, matter is the stuff the universe is made of. It can be solid and hard like a stone, flowing like a river, or even entirely invisible like the oxygen we're breathing right this second. If it takes up space and has mass, boom, it's matter. Now, it's pretty easy to point at a piece of chalk, a brick, or a glass of water and know it's matter. But think about light or sound. If you shine a flashlight or shout across a room, you're definitely producing something, right? But light and sound are not matter. Why? Well, try putting a shout on a weighing scale. You can't. And light doesn't take up physical space in a container. They are actually forms of energy, not matter. Moving right along to Section 2, Properties of the States. If the stuff around us is matter, how do we tell the different forms apart? We just look at how they physically behave. Think of a solid, like a stone. It has a completely fixed shape and a fixed volume. There's literally no way you're compressing or squeezing a stone into a smaller size, and you definitely can't pour it. But liquids, like water, they keep a fixed volume, sure, but they magically take the exact shape of whatever you pour them into, and they flow so easily. Then we have gases, like the air. Gases are kind of the rebels here. No fixed shape, no fixed volume. They just expand to fill up any space you give them. Because of that, you can actually compress or squeeze them down into a much smaller space, like packing air into a bicycle pump. Oh, and I absolutely have to mention the wild card, the highly energetic fourth state of matter, plasma. This is a superheated state. You're not exactly cooking with it in your kitchen, but you for sure see it. Plasma literally makes up the sun, and incredibly, it's created right here on Earth inside lightning bolts during those huge, heavy thunderstorms we get. It's wild stuff. Section 3. The kinetic theory explained. Okay, so we know how solids, liquids, and gases act. But to really get our universe, we need to zoom way in and ask why they act so differently. The answer is the kinetic theory. This is the scientific idea that absolutely all matter is made up of these tiny, completely invisible particles that are constantly moving. The key word here is kinetic. Kinetic means movement. Think of the chaotic energy of a boda weaving through crazy traffic. It's just always in motion. That is exactly what the microscopic particles inside your desk, your cup of tea, and the air around you are doing right now. Let's use a quick school analogy to make this crystal clear. In a solid, those tiny particles are like students packed tightly together on a single wooden bench. They're held there by really strong forces, so they can't run around. They literally just sit there vibrating and wiggling in place. That's why a stone is so hard. Now, picture a liquid. The holding forces are way weaker. The particles are more like students walking past each other in a crowded hallway. They're close, but they can easily slide past one another. And a gas? Ugh. A gas is break time. Almost zero forces holding them back. It's just particles running completely wildly all over the football pitch in every direction. Section 4. Heat gain and heat loss. So what happens when we introduce temperature to these moving particles? Let me ask you a trick question that catches almost everyone out. When you heat up a solid, like let's say you toss a piece of metal into a fire, do the individual microscopic particles inside it actually get bigger? No, absolutely not. The particles themselves stay the exact same size. So what's actually changing? Well, the heat acts as pure energy. It pumps up those tiny particles so they move much faster.
And because they're vibrating with so much crazy energy, they physically shove each other further apart. It's the empty space between the particles that expands, not the particles themselves. Let's walk through the steps of adding that heat. Step 1 is melting. You add heat to a solid, giving those tightly packed particles enough kinetic energy to finally break free from their rigid, vibrating positions. And boom, it turns into a liquid. Step 2 is boiling, or evaporation. You keep adding heat, and those liquid particles gain so much kinetic energy they completely overwhelm the forces holding them down, literally launching into the air as a gas.
We can map this whole journey perfectly using something we see every day: water. Down at 0 degrees Celsius, solid ice gains enough heat to melt into liquid water. As that temperature ramps up to, say, 50 degrees, the liquid particles are just sliding past each other faster and faster. And then, when we hit 100 degrees Celsius, those particles have absorbed so much kinetic energy, they boil and evaporate right into steam. The amount of heat input entirely dictates what state the matter is in. Which brings us to our final section, Section 5, the cooling magic of evaporation. Let's pull back to our everyday macro world and see how these frantic, invisible particles actually affect our comfort and our survival. Evaporation is basically a magic trick. It's a process where a liquid changes into a gas below its actual boiling point. But here is the secret. To make that jump from liquid to gas, the water particles desperately need kinetic energy. They need heat. So where do they get it? They literally steal that heat from whatever surface they happen to be touching. This is exactly why sweating is a biological superpower. When you're standing in the hot sun, your body pumps out sweat. As those liquid sweat particles evaporate into the air, they absorb and carry away your actual body heat, cooling you right down. It's the exact same science behind those traditional clay water pots. The water slowly seeps through the tiny pores in the clay. As the hot outside air evaporates that surface water, it robs heat from the pot, leaving the drinking water inside wonderfully cold. And what about that wet school shirt on the line? The hot sun and the blowing wind are just feeding kinetic energy to the water particles until they escape, leaving the fabric perfectly dry. Okay, real quick, before we finish up, I gotta bust one more massive myth for you. When you boil a kettle and see that thick white cloud pouring out of the spout, literally everyone calls that steam. But actually, scratch that. It is not steam. True steam is a gas, and it's completely invisible. You cannot see it. That white cloud, that's condensation. It's the invisible super hot gas hitting the cooler room air, rapidly losing its heat energy, and instantly turning back into millions of tiny liquid water droplets. You're literally watching a change of state happen right before your eyes. All right, here is your final challenge for today. I want you to take everything we just talked about, matter, particles, heat, and solve one last mystery. If you leave a fully inflated football out in the blazing afternoon sun, after a while, it's going to feel much harder and way tighter. Using the kinetic theory of matter, what exactly are those invisible gas particles doing inside that football to make that happen? Think about the kinetic energy, the empty space, and the movement. Keep that bouncing around in your head next time you step out into the sun. Thanks so much for joining me on this explainer, and hey, keep questioning the world around you.